What is up, everyone? Mr. Schleicher here. I actually recorded this entire video and realized I didn't have any sound. So this is me voicing over what I recorded already. So today we are going to learn about this new concept called mole ratios. Actually, one of my favorite concepts in chemistry. I just love all the math and fractions. So our learning goals right here are we're going to define what a mole ratio is. We want to convert from number of moles of a reactant or product to the number of moles of any other reactant or product. And we're going to do all of this by using dimensional analysis to convert from grams or particles of any reactant or product to that of another reactant or product. So what do we already know about dimensional analysis? Well, it's a useful tool for converting between two equivalent values. The other thing here is that the top and the bottom number in any sort of ratio that we make has to be equivalent. For example, maybe we have 1 dozen is equal to 12 eggs. Now, 1's not equal to 12, but when you add those units, dozen and eggs, it actually does become equivalent. So let's try practicing this problem here. And if you feel like you got it, try it without looking at the video. If not, here we go. We want to convert 26.2 miles to meters using dimensional analysis, just knowing that 1 mile is equal to 1.6 kilometers. So we already have a conversion factor. We know what we're given, 26.2 miles, and we know we're being asked for meters. So using dimensional analysis, we are just going to write down what we're given first. So that is going to be that 26.2 miles. And we're trying to convert to meters, but we don't know how to get to that in one step. But we do have this conversion factor already. We know that 1 mile is equal to 1.6 kilometers. So we can put 1 mile on bottom here, so it cancels out with miles on top of our last number. And we're going to convert that to 1.6 kilometers. Now, how do we get from kilometers to meters? Well, a kilo is 1,000 of something, so it has to be 1,000 meters in a kilometer. That's our conversion factor there. And then finally, we are going to plug this into our calculator. So that is going to be 26.2 times 1.6 times 1,000. Pretty simple. We can also divide by 1, but I mean, come on, that's kind of redundant. And then we're going to get our number after calculating, which should be about 41,900 meters here. Moving on, so what do we already know about chemical equations? Well, the reason why we add chemical equations is we wanted to show that this law of conservation of mass showed that we had an equal number of each type of atom before and after our chemical reaction happened. But it can show those atoms arranged differently. We actually saw this in action when we were balancing our chemical equations, just to make sure that the number of each type of atom were equal before and after. So we actually want to make sure that we're always dealing with balanced chemical equations. Otherwise, our calculations that convert between one atom to another don't really make sense. So what are mole ratios? Talking about ratios, let's think about different examples of ratios first. So before we did say that 1 dozen is equal to 12 eggs, or maybe we could say that 60 seconds is equal to 1 minute, or 365 days is equal to 1 year. Either order doesn't really matter, just the fact that we're setting up these ratios and we're able to use them and make these numbers equivalent just by making the units different. So we get our mole ratios from a chemical equation, and this mole ratio is the relationship that tells us the ratio of moles or particles between any two chemicals involved in the chemical reaction. Very useful in these types of problems that we're about to do. So the coefficients in our chemical equation tell us the number of moles in our ratio. So those numbers at the start of our chemicals in our chemical equations that we change to balance it, very important here. So let's look over here at this combustion of methane, or CH4, in oxygen gas to produce carbon dioxide in water. Has this beautiful picture. You can just see how all these different atoms take up space, and we actually have the right number of atoms here, and then the balanced equation below this picture. So in this actual chemical equation, we can look at these coefficients, and we know that since there's no coefficient, there's 1 mole of CH4, and for every 1 mole of CH4, we have 2 moles of oxygen, 1 mole of carbon dioxide, and 2 moles of H2O, water. So from these numbers, we can come up with some mole ratios. Some possible mole ratios that we could think about are 1 mole of CH4 to 2 moles of O2, or 2 moles of O2 to 2 moles of H2O, or maybe 1 mole of CO2 to 2 moles of O2. See, I'm basically just making all these up. You can have so many possibilities, just making sure that they're relevant to your problem. Now these ratios work for this reaction only, so you got to make sure you come up with new ones if you're dealing with a different chemical reaction. Looking at these ratios, it really allows you to predict the amount of each product that you're going to produce. So for example, let's look at this problem. How many moles of water will be produced when 25 moles of methane are combusted in excess oxygen? So we're looking for moles of water, and we have 25 moles of methane. So remember, methane was CH4. Let's start with 25 moles of methane in our problem and use a mole ratio to convert it to moles of water. So according to our chemical equation, it said that we had 1 mole of that CH4 for every 2 moles of H2O. So let's plug that into our equation and make sure we cancel out moles of CH4. Very important that we're writing our chemicals and units for everything here so we can keep track of what's going on. All that's left is to calculate this, and 25 times 2 should equal 50 moles of H2O here. Okay, so for this final part of this video, we are just going to go through a bunch of different problems that you'll be expected to be able to solve. So I recommend that once you think you get the idea, try these on your own, pause the video, see what you can do. We do have a basic problem solving strategy for problems like this when we do these different chemical to chemical conversions with chemical reactions and chemical equations. Number one, we always want to have a balanced chemical equation, so we're looking for that first. Number two, we want to make sure that whatever we have is converted to moles before we do anything else. Number three, we're going to set up some mole ratios so that we can solve this problem. Number four, we're going to get to the moles of the desired chemical that we want. And five, we'll do a final conversion if we need to. So let's look at this first problem here. Write the correct mole ratio for the moles of TNT to moles of N2 gas. Now that TNT is that really complicated first highlighted molecule there. So it looks like the coefficient's 4, so 4 moles of TNT, and then N2, 6 moles of N2 gas. That is our mole ratio. Next question. 35 moles of KMnO4 are present in a sample that is mixed with excess hydrochloric acid, or HCl, according to the reaction below. How many moles of water would you expect to be formed? Okay, so we're starting with 35 moles of KMnO4, and we're trying to convert it to moles of water. So we're going to write down what we have first and use a conversion factor to get to moles of water. Now, we know that there are 35 moles of KMnO4, and then in a chemical equation, there are just 2 moles of KMnO4. So we're going to put that down there to cancel out with the initial moles that we had. Now we're going to look for water. It looks like there are 8 moles of H2O in that equation. So we're going to put that on top and then solve this problem. So 35 times 8 divided by 2 should get us our answer in number of moles of water. And as you can see, the number of moles of KMnO4 did cancel out. After calculating this, you should get about 140 moles of H2O. Next question. The explosion of nitroglycerin is shown below. How many moles of carbon dioxide are produced when 5,100 grams of nitroglycerin explodes? So nitroglycerin is this giant complex molecule on the left there. We're starting with 5,100 grams, and we got to figure out how to get to moles of carbon dioxide. We're going to abbreviate nitroglycerin here with an NG, just too much to write. You're allowed to abbreviate things as long as you label them and you know what the abbreviation means, and it's really obvious. And the first thing we're going to do is convert these grams to moles. How do we do that? We got to find the molar mass of nitroglycerin. So unfortunately, the only way to do that here is to actually look at this molecule of nitroglycerin that they give us and count up every single little atom and add up all their atomic masses together. So it looks like there are 3 carbons. So we can do atomic mass of carbon times 3. There are 5 hydrogens. There are 9 oxygens and just 3 nitrogens. So we're going to find the atomic masses of all of those and add them up together, multiply them out. And I actually knew all these from memory, but of course you're allowed to use your periodic table. So in your calculator, in one line, all you have to do is put in 12.01 times 3, plus 1.01 times 5, plus 16 times 9, plus 14.01 times 3. Just these masses of these elements from the periodic table times the amount that we found in that actual picture. So after calculating that, we should get the molar mass of nitroglycerin that we can use to finish solving our problem. And that number is 227.11 grams per mole of nitroglycerin. We're going to put that back down there in our dimensional analysis, and now we can actually convert from grams of nitroglycerin to moles of nitroglycerin. However, we're still looking for moles of carbon dioxide. Now, we have moles of nitroglycerin. We can use a mole ratio according to our problem here to convert from nitroglycerin to carbon dioxide. So let's go ahead and do that. It looks like there's 1 mole of nitroglycerin for 3 moles of CO2, carbon dioxide. Plugging that in to cancel out moles of nitroglycerin, in our calculator we should plug in 5,100 divided by 227.11 times 3, and that should equal moles of CO2, which is about 67 moles of CO2 here. That's what I got. Excuse me. All right, next question here. 50 grams of iron react with excess oxygen to form iron 3 oxide as shown in the reaction below. How many moles of iron 3 oxide are produced? Okay. And then we are given a balanced chemical equation here. So very similar to last question, we start with 50 grams of one chemical, and we're asked for the number of moles of another chemical. Now that iron 3 oxide, it is that Fe2O3. Don't need to make any sort of chemical writing there. And we can go ahead and set up our dimensional analysis. We're given 50 grams, so we're going to write that down. And we're going to go ahead and try to convert that to moles of Fe, or iron here. Now the molar mass of iron, I believe that's 55.85. So we're going to write that down, 55.85 grams of iron in 1 mole of iron. And the question is asking us for moles of iron 3 oxide. So we are going to look for the mole ratio there. Canceling out moles of iron, let's put down 4 moles of iron because that's in our chemical equation. For every 2 moles of iron 3 oxide. Now you might be asking, why is it iron 3 oxide? There's not 3 irons, but that is because iron 3 is the charge of iron. There are 2 Fe3 pluses that cancel out 3 of those O2 minuses. Okay, so finish calculating this. That is going to be 50 divided by 55.85 times 2 divided by 4. And then we should get our moles of our iron 3 oxide, which is about 0.4 moles of Fe2O3. In our next question, an unknown quantity of ammonium phosphate is reacted with excess barium nitrate to produce 500 grams of ammonium nitrate, or ammonium phosphate. So how many moles of ammonium phosphate were in the original sample? We're going to be backtracking a little bit here. We're actually starting with the amount of a product, and we're working back to the reactant here. Now, all these names, these are polyatomic ions. So ammonium is NH4 plus, phosphates at PO4 minus, nitrates NO3 minus, just looking out for stuff here. We are given 500 grams of ammonium nitrate, so 500 grams NH4NO3, and we do need to convert that to moles before we continue solving this problem, which means finding the molar mass to get from grams to moles. So the molar mass of our NH4NO3, I think it's the wrong arrow there. Just count up the number of N's. Looks like there's 2 N's. There's 4 H's and 3 O's. So find the atomic masses for those elements. 14.01 for N, 10.01 for H, 16 for O. Multiply them up and add them together in your calculator. 14.01 times 2 plus 1.01 times 4 plus 16 times 3 should get you about 80.06 grams of ammonium nitrate per mole. And we can use this conversion factor in our dimensional analysis now. So we're going to go ahead and do that. 80.06 grams of NH4NO3 can cancel out our initial number of grams. And now we can convert to moles of our ammonium phosphate, which is what we're looking for, that NH4 3PO4. So let's look at those coefficients. It looks like 6 moles of NH4NO3 for every 2 moles of NH4 3PO4. Plugging that in to make sure everything cancels out correctly. Now we can calculate 500 divided by 80.06 times 2 divided by 6 should get us our answer in moles of NH4 3PO4, which rounds out to about 2 moles of that ammonium phosphate. All right, final question. Uranium hexafluoride reacts with pure sodium in a single replacement reaction. How many grams of pure uranium, a little bit typo there, can be extracted from 2.000 grams of uranium hexafluoride? So we need a balanced chemical equation to solve this first. Just write out the chemicals. UF6 is that uranium hexafluoride, plus sodium is Na. Single replacement, I'm thinking, I've seen Na with F before, so I think Na is going to replace uranium here and make NaF. And then uranium is going to be all by itself afterwards. You could think of that as like a way to extract uranium. Still got to balance it. 6 F's on the left side, so making sure there's 6 on the right. Now there's 6 Na's on the right side, so put 6 on the left to balance that, and now it looks balanced. So let's go with what we're starting with. 2.00 grams of uranium hexafluoride. And then we're trying to go to grams of pure uranium. So let's start out with 2 grams UF6. And we got to convert to moles of UF6 before we do anything else, before we can convert it to moles of a different chemical. And in order to do that, yes, we got to find that molar mass again. So the mass of one of those U's and 6 of those F's. Adding them together. And you can find those atomic masses just from your periodic table. The mass of uranium should be 238.03. And then the mass of a fluorine, an F, I think it was 19. So 6 times excuse me there, 19. So adding that all together, we should get our molar mass of UF6. We gotta drink some water after this. Okay, so our molar mass was 352.03 grams of UF6 per mole. We can plug that in to cancel out our grams of UF6 and convert to moles of UF6. But the question's not asking us for just that. We gotta get to moles of, now we have to get to grams of pure uranium. But before we can do that, let's get to moles of uranium first. It looks like in this equation, it's just a 1-to-1 mole ratio. So we're just writing 1 mole UF6 to 1 mole of U. And then moles of UF6 are canceled out. How do we get from moles of U to grams of U? We got to figure out the molar mass of uranium, which we figured that out already. That was 238.03 grams in each mole of uranium. So we have set up our problem, and now we can calculate it. That is going to be 2 divided by 352.03 times 238.03, and we should get about 1.352 grams of uranium.